Okay, welcome Ralph and Jesus and Cesar and Jordan and Victor to the linear algebra class. Let me share my screen and we'll talk about what we're doing today. Okay, so here's the plan of the day. What we'll do is we'll start out with Q&A as always. And then after that, you took your exam and I graded it and I'll talk about it a bit. I've actually posted the exam and key that you can take a look at, and we'll kind of look through some of it, not all of it, because that could take a long time. And then after that, if you remember on Monday, we talked about linear transformations and we defined what a linear transformation was. So today we're going to get into properties of linear transformations. That's what we'll start with. So we'll say, if you have a linear transformation, what do you know about it? And then we'll realize that a linear transformation is a function. And as soon as you know it's a function, that means anything you can say about functions is true about linear transformations. So we'll think about it that way. And in particular, we'll be able to look at a linear transformation as a function and then realize that it's a matrix and then combine the two. So we'll look at linear transformations and their matrices, and then we'll be able to think about what is the inverse. Since a transformation is a function, what's the inverse of that function? And then we'll say things like, what is the composition of two linear transformations? Okay, since functions have compositions. So we'll do all that stuff. And then after that, we're going to get into a little exploration about matrices. And it's one of my favorite parts of the class because it's like cool stuff you can do and useful and fun. So I'll talk about it. And in particular, we'll look at a couple. We'll look at rotations, and we'll look at sums of angles and a few other things like reflections. And that is the plan for today. So let me know if you have any questions. This is a really good time. There's homework due today. I'll go over the test in a bit. So if it's about that, we'll see that in a second. But any questions about the assignment or anything else? Any questions? Give you a moment to think. Yeah, homework is fine. When I say assignment, I mean homework. I just don't use the word homework in this class because your test was homework also, right? Didn't you do it at home? So the word homework doesn't work in this class. So that's why I call them assignments, means the things that you have to turn in that aren't exams. So number 13 first. And let me see something. So I guess you mean 5.2, right? Because there's two sections due today. Okay, so 5.2, number 13. Let me go find it. Okay, just a minute. Okay, so here's 5.13, section 2. And it says the following. Find the matrix for T of W, which is a projection of V onto W, where V is the 103 vector. Okay, so we need to find the matrix for that. Okay, so we want to project onto V. So to do that, we need to find out what does T do to the elementary bases. So for example, let's start out with 1, 0, 0. Okay, and I guess I should make them in pointy brackets because they're vectors. So do you remember how to find the projection of a vector onto 103 transpose for 100? Do you remember the formula? I don't hear anyone talking. I don't see any writing. So hopefully you can hear me. So how do you find the projection? I guess I shouldn't write equal. I should write projection.
It was B transpose times B.
Yeah, we're just talking vectors. We're just talking vectors, so we just take a dot product, right?
Oh, yeah.
So what's the dot product? What's the dot product of the 0.100 with 103? It's very easy.
Just
1.
4.
Yeah, it's 1, right? And then we're supposed to divide it by?
The magnitude of our vector.
Yeah, which is? And it's the magnitude squared of the vector, right?
10.
Yeah, 10. Times 1, 0, 3. Any questions on that? Okay, and that's quite easy. That's equal to 1/10, 0, 3/10. Any questions so far? So now let's do, maybe I'll put a colon, I guess, might be better. There we go. 0, 1, 0. And we're going to project it onto the vector. Okay, so now it's a dot product. It's very easy.
It's 0.
Yep, it's 0. And we're going to multiply that by 103. And I guess technically you're supposed to divide by the magnitude, but I'm multiplying by 0, so I don't really care. Because you just get 0, 0, 0. There is a 1/10 in there, but who cares when you're dividing by, when you're multiplying by 0. Okay, then we have 0, 0, 1. I'm just doing the standard basis. And the projection is, well, take a dot product. What do you get?
It's 3.
Right, you get 3, and then times 3, and then it's still over the magnitude over 10. Okay, and then we're going to multiply that by 1, 0, 0, 3. And what we get is 3/10, over 10, 0, 9/10. Did I lose anyone there? Okay, once we have that, now it's easy. What's the matrix? How do we get the matrix? Because that's what we want. That's what we're
Set up
after.
those 3 vectors we just found as column vectors.
Yep, and that's it. So let's do that. Insert equation. Let's go to bracket, paren, drop matrix, and it's a 3 by 3. We just set them up. 1/10. Zero. I forgot to put the over on the third one. 0 and 3/10. And then 0, 0, 0. And then 3/10. And then 0. and then 9/10. Any questions on that? Was that easier than it looked? Is that clear now? Okay, there was a question about number 10 also. And my guess is same section because I think the other section didn't go that high in terms of questions that I asked. So let's go to number 10. So let me pop in number 10. Okay, so here's number 10. And that is, suppose we have A1 through AN inverse exists where each AJ is in Rn. So in other words, we have a bunch of column vectors, and then the inverse exists. And let the vectors B1 through Vn in Rn be given. Show that there always exists a linear transformation from T such that T of AI equals Bi. Okay. So how do we go ahead and do that? Any suggestions?
I was thinking maybe we could start out with AI and J, and BI and B and J, and go from there, starting as a full matrix instead of just either a row or column.
Okay. So when you say a full matrix, which matrix are you talking about?
So instead of T of AI, make it T of AIJ, and same with B.
Yeah. Well, T of AIJ, there is no such thing as AIJ.
Okay.
AI is a column and T is a, see, the thing is, T is a linear transformation that sends things in Rn to more things in Rn.
Can we do
What's that?
matrix transformations?
Yes, we need a matrix, right? Okay. So we want to make sure that we have these B's and we want to send them to the B's. Okay. And we want to say that T of AI equals BI, right? So what matrix do you think we'll use for that to make that work? So I'm going to just let A be the matrix of, I'm going to write even to stress it, invertible matrix, invertible. Whoa. I had it right. The invertible matrix of the AIs. Okay, any questions on this so far? Just to name it. Okay, we know A inverse exists, right? And we need to make sure that T of AI is equal to BI. So the idea is if A inverse exists, what does that mean? What does that tell us we can do?
We can find a matrix of T.
Yeah, we can find a matrix of T, but more importantly, I can use TFAE. And state that the AIs form a basis. Any questions on that? That was part of TFAE, is that if the inverse exists, then the columns form a basis for Rn. Everyone okay with that? I don't know if you remember every element of TFAE, but that was one of them. Well, if they form a basis, now I can consider that as the basis. Okay, and we've learned if we know where the T sends a basis, then we always know how to find out what the matrix is for T. And that is you take the inverse of that matrix where the column vectors are the basis vectors. Any questions on that? And multiply by the B's. So then the matrix for T is A inverse. Let's see. Yeah, I think I should probably make it look prettier. So insert symbol math. So A inverse times B. Do you remember doing this? I know it's been 4 days and you were thinking about the exam, but that's exactly what I did 4 days ago. Is I said, if you have a basis, then, and it's the inconvenient basis. So the AIs are the inconvenient basis for Rn. Then you can always take a linear transformation, find its matrix by taking the inverse of the matrix of columns times where those columns go. Anyone lost on that? And this is it's called proof by construction. So if I can say, here's how you get the matrix, then I've proven that you get a matrix. Do y'all agree with that? Any questions on that? Any questions? Okay, if there's no questions, then I'll move on. You're being a little quiet. Any other questions before I move on? If not, that's okay too. So we have plenty to do. Okay, if there's no questions, I think I want to go through the exam, and not every detail, but just kind of quickly. So let me reshare my desktop so that we can see the exam. And I'll show you how to find it. I put it up this morning, I believe. So if you go to, where did I put it over here, I think? Key. And I'll preview the document. Okay, and let you know, like all exams, some people did better than others. There's a good group of A's, but there were some that struggled a little bit. So it's, it is what it is. But note that it's not over even if you struggled, because you still have 2 other exams. And you also have your presentation, which it's too early to even, talk about. That's the last week of class. So I want to quickly go over, and I want you to do, since I'm going to quickly go over these, if there's anything you want me to slow down on, tell me to slow down. The ones that a lot of people have trouble with, I'll go slow, but the ones that most of you got, I'll just go fast. Okay, so question number 1 is you can't use technology, and you need to write the matrix below in RREF. So the key, and some people didn't get, is you have to use elementary row operations. Okay, so pretty much most of you got this one right. And you can see the matrix that you end up with. And that is 1, 0, 2, 0, 1, 0, and 0, 0, 0. Any questions on number 1A? Okay, 1B. So 1B, and this is important, you have to find, and I put it in bold, the easiest row or column. Which is the easiest row or column in this matrix?
Column 2.
Yeah, column 2. Okay, not row 1, by the way. Row 1 is the way the computer does it. And what I purposely did is made sure that doing it by hand was easier than the way the computer does it, and the computer will never do it the easy way. So that's why I forced you to do it the easy way. Okay. So you have to do it with column 2 or you don't get full credit. And the nice thing is it's just 0 plus 0. And then this 3 is in row 3, column 2. So it's going to be 3 times -1 to the 3 plus 2 times the matrix obtained by getting rid of its row and column, which is 2, 4, 1, -1. And then the determinant of 2, 4, 1, -1 is just going to be 2 times -1 minus 4 times 1, and you just plug in, you get 18. Any questions on problem 1? Okay. And I didn't think it was that unreasonable asking you to do by hand, because I tried to give you one that was not miserable. Do y'all agree that that wasn't miserable?
Yeah.
Okay, I really worked hard on that. Actually, it took a while to find a good one, in both the RREF and in particular one where the computer wouldn't do it the way I asked you to do it. The computer gives you all kinds of fractions in the steps, and that's because it uses the computer programming way of doing it, whereas human brains think differently. Okay, so let's go to number 2. Number 2 was the hardest question on the test for sure, because let's see, because it had that one word that a lot of people have trouble with. What's the hard word on number 2?
Prove.
Prove. Not all of you are there with proofs yet. Okay. So there's a few ways of doing part A. First thing, notice that they're n by n matrices. You can't assume n is 2. That's not a proof. You can't write down a 2 by 2 and then show it doesn't work with 2 by 2s, because you've maybe proven it for 2 by 2, but what about 12 by 12s or a million by a million? So a proof in this case has to be general. And the way you do it is you do a plus b squared, which is a plus b times a plus b. Now you're allowed to use the distributive property, because that is the property of matrices. And then you get a squared, or if you want a times a, plus a times b plus b times a plus b times b. So then you need to realize that AB and BA are not the same in general. Got it? Okay. Sometimes they're the same, sometimes they're not. Okay. And by the way, they're the same for a lot more than just the identity, but they're not the same for a lot of matrices. So in particular, when you compare a squared plus 2ab plus b squared with a squared plus ab plus ba plus b squared, then we're looking at a plus b plus b plus a, and that's not 2ab, because then ab equals ba. Any questions on part A? Okay, part B. Okay. Here's what you're not allowed to do. And some of you did this. You're not allowed to say, well, it's true because a theorem says it's true. Because the whole point is you're proving the theorem. Any questions on that? And some of you did that. Some of you said it's true because if A, B are invertible, then A and B are both invertible. Well, that's not a proof. That's just restating it. Any questions on that? What you can do is you can take the determinant of A times B, and the determinant of A times B is the determinant of A times the determinant of B. What you can't do is say AB inverse equals equals B inverse A inverse, because that assumes B inverse and A inverse exist, and it's circular reasoning to say therefore A inverse and B inverse exist. But you can do the determinant because that's not circular. And then you can use the rule of numbers. Okay, that we know that determinant of AB is non-zero because AB is invertible. Okay, that's part of TFAE. And then the rule of numbers said that if 0 equals a product of two things, one of those two things must be 0. Therefore, the determinant of A and the determinant of B must be non-zero, because of 1 and 0, you get 0 when you multiply. But if they're both non-zero, then TFAE again says that they're both invertible. Any questions on part B? A lot of people had trouble with that one. A lot of you did circular reasoning, which is not so good. Okay, let's look at part C. And that is if V1 through VK are linearly independent with K greater than 2, then the set V2 through VK is also linearly independent. Again, most of you got the true false piece right. The proofs were hard. To show something's linearly independent, you need to start out with the summation of CI VI. So in this case, since we're looking at V2 through VK, then we're looking at C2 V2 plus ... CK VK equals 0. Any questions on that? That's how a proof has to start. But then I can add 0 V1 because that doesn't change in addition. I added 0 to the left-hand side. But now I have something of the form a constant times V1 plus a constant times V2 plus ... plus a constant times VK. Okay. And we know that this first set is linearly independent. So therefore, all these constants are 0. Of course, the first one's 0 because it says 0. But more importantly, C2 is 0. All the way to CK is 0. So that means that all of these guys are 0. And that's a definition of linear independence, is that if you write down this equation, C2 V2 plus CK VK equals 0, then all the C's are 0. So therefore, the second set is linearly independent. Any questions on the proof? Okay, again, the hardest part for many of you were these proofs. Okay, now let's go to part D. If V and W are in the span of S, where S is V1 through VK, then V plus W is also in the span of S. So again, you can't just say it is because we've added, so it has to be. That's not a proof. Okay, to show that V plus W is in the span of S, we need to write V plus W as a linear combination of vectors in S. Okay, any questions on that? But if V and W in the span of S, V is a linear combination of vectors in S. So V equals C1 V1 plus C2 V2 plus ... CK VK. And W is in the span of S. So W is equal to, I probably should say D1, but it's actually okay because there's no other D's. dV1 plus D2 V2 plus ... plus DK VK. And now you just add the two. V plus W. Well, if you add them, you can combine like terms and you get C1 D plus D1 times V1 plus C2 plus D2 times V2 plus ... plus CK plus DK times VK. And that's in the span of S because it's constants times the vectors added together. And that's the proof. Any questions? Any questions on the proof there? Okay, again, this is where a lot of you had troubles. Okay, let's go to E, the last of the proof questions. Okay, and by the way, if it's true, are you allowed to do it by example?
No.
Never. Okay, proof by example never works with truths. But falses, on the other hand, proof by example is what you want to do. It's very hard to prove without by example on a false. So we want to show if if A is an orthogonal matrix, then A is also an orthogonal matrix. Okay, so I grabbed, you know what, this one, sorry about that. This one doesn't work. I can't change it now because this one's actually not, let's see. Oh no, this does work. Sorry, I made a mistake. A is equal to 2, 0, 0, 1. Okay, A is not orthogonal because notice the first column, has magnitude 2, and that's not magnitude 1. And orthogonal means the magnitudes have to be 1, magnitudes of the columns. But RREF of A is equal to the identity for lots of reasons. One is the determinant is 2, so that's by TFE. RREF of A is the identity. Okay. Or you could just do one row operation, divide by the first row by 2 and get the identity. So, and that is orthogonal, therefore it's false. Because I have an example where it shows that it can't be true. Any questions on E? Okay, again, without an example, this isn't going to work. And there are a group of you did not give an example. Okay, now let's go through the rest of the test, which is a lot easier for most of you. Okay, so we have a chemical reaction, and most of you got this right, so I think I'm going to go through this really fast. Is you write down the matrix that comes from this chemical reaction by letting the coefficients just be x1, x2, x3, x4, x5, and then this is the matrix you get, and then RREF the matrix. Don't even think about doing it by hand. You're allowed a computer to RREF, and this is what you get. And now note, because it's chemistry, you're not allowed to use 1 because then you get 1/4 over here, and you're not allowed to have fractions because that's like against the chemistry rules. So instead, we can let the last one be 4, which is a common denominator or the denominator, and you end up with this. Any questions? Okay, next one. Okay, determine which of the following vectors span R3. You must show your answers correct. So most of you got that you take the matrix of column vectors and RREF that matrix, and you get this beautiful matrix right here. And then what you do is you count the pivots. A few of you are confused between linear independent and span. Okay, span means you count the pivots and you have to make sure that you have n of them. N is 3 in our case. So I have 3 pivots. So it spans R3. Any questions on this example? I mean, this problem. Okay, just a note, by the way, is it guaranteed that B does not span R3 because A did?
No.
No.
Yeah, that's not okay. You can't just say, oh, A spans, so B doesn't. No, because it didn't say that one spans and the other doesn't, which one spans. It just said determine which span. So basically you do the same thing and you write down the matrix of column vectors. You RREF. And then we count the pivots, and guess what? There's only 2. Okay, and 2 is not enough pivots to span R3. So therefore, T does not span R3. Any questions on problem 4? Okay, problem 5. Again, I'm going through this fast, so if you have questions, please stop me, because I'm going fast because I don't want to waste your time either. Okay, so problem 5 is exactly the same, except it's about linear dependence instead of about span. So you start out exactly the same way. You write down the matrix, you RREF it. Now it's not about counting. It's not about counting the pivots. Now it's about looking at free variables. And here, there are no free variables because every variable, all 3 of the columns are pivot columns. So because of that, there's no free variables, so then only the trivial solution exists, so they're linearly independent. Any questions on part A? Okay, part B, on the other hand, if you write down the matrix and then you RREF it, then you realize this third variable is a free variable. So since the third variable is a free variable, they're linearly dependent, because if you have a free variable, you have dependent. Any questions on that? So then it's a matter of writing these down and realizing that we have 3 variables. The third one's a free variable, so you can let it be anything you want. So I let it be 1. I mean, you could let it be 9 if you don't like fractions if you want. And then you can get this without those fractions, at least to start. But I let it be 1. And then realize that we have an equation here. Okay, so what we get is, this is saying that the first variable is plus negative 7/9 times a third is 0. So that means the first equals 7/9 times a third. So that means we have a positive 7/9 times 2, -1. And similarly, we're going to have a negative 5/9 times negative 1/4 plus 1/3 is equal to the 0 vector. So now you just solve for 1/3 and you get 1/3 equals negative 7/9 times -2, -1 plus 5/9 times -1/4. Any questions? Any questions on part B? So I found part B was harder than A for most of you. Okay, let's go to number 6. So number 6 is we have this T. And we need to find a basis for the column space of T using only columns of T. So you RREF T. And you get this beautiful matrix. And notice the pivot columns of the first, the second, and the fifth. Most people got that, which was nice. So that means you just write down the first column, the second column, and the fifth column. And there's a basis for the column space. Any questions on part A? Okay, the null space you had more trouble with. So the null space is a little like problem 5B, where you got to realize that when you RREF, you get the same null space. And these are equations. This says first variable times 1 times first variable plus 0 times second variable plus 1 times third variable plus 1 times fourth variable plus 0 times fifth variable equals 0. And the third and the fourth variable are the free variables. So that means that for the first basis item, we're going to let the third be 1 and the fourth be 0. And when you do that, you get -1, because here we have a x1 plus x3, which is just plus 1 equals 0. So then that gives you -1. Similarly, you get a 2. And again, we let the third variable be 1 and the fourth be 0. Okay, and the fifth is just 0 because this equation here says the fifth variable times 1 times the fifth variable equals 0. So fifth will be 0 in both of these. And then for the second basis vector, you let the fourth variable be 1 and the third be 0. And that gives you -1, -1, 0, 1, 0. Any questions on part B? Because some of you had trouble with that one. That was the hardest part of this problem. Okay, then it's a matter of counting. The rank is going to be the number of column vectors that are pivot columns, and that was 3. Okay, and the nullity, without even looking at part B, how do we know the nullity has to be 2 once you know the rank is 3? Do you remember the theorem?
Rank plus nullity must equal the number of columns.
Exactly. So that, and the number of columns, I hope you can count, is 5.
5.
So 3
At least
plus
in this
something is
example.
5. So that means that something must be 2. Yeah, rank plus nullity is equal to n. In that case, 5. Any questions on number 6? Okay. By the way, I figure I put this up here not to confuse you, but this is the one that would have happened had I not shortened the exam. But I think I made the right choice because I saw, I think 3 of you had comments, I'm running out of time. And if there was even another one, then it would have been much worse. So I'm glad I got rid of problem 7. So just let you know, that would have been problem 7, but it wasn't. but I figured I'd leave it up there just so you can kind of see what I was originally thinking before I got rid of it. So, but I'm not going to go over it. Okay, and then problem number 8, okay, which was your new problem 7, is use linear algebra to find the least squares line y equals mx plus b for this data. All right. The funny thing is, I looked at how you were doing it, and it's like, whoa, you're doing it in a really hard, awful way. And then I realized that was the book. The book did it 2 ways, and you guys did it in the hard, awful way, most of you. I think one of you did it in the easy way. The easy way is to write down your A, and that just means plug in. So we have mx plus b. So remember, m and b are what you're solving for. So the coefficient of m will be the x's, 3, 2, 4, and 0. And the coefficient of the b's is always 1, 1, 1, 1, 1. Call that A. And then just go to Symbol Lab, put in A transpose A inverse times A transpose. It gives you this. Then multiply by 1, 1, 4, 2. And you get 21 35ths, 43 35ths. And that's your m and b. So y equals 21 35ths x plus 43 35ths. So again, given the fact that you have Symbol Lab, this was the easy way and the way I was hoping you do it, but a lot of you did it a much harder way. Any questions on this process, this way of doing it? Any questions on that? Okay, and this is how you get the equation of the regression line. Okay, and the last one was extra credit, which most of you did. Again, if you didn't, I can't give you points for it. But those of you did, I'll mention, let me get my notes out on what you said. There were some things, and honestly, I don't have a whiteboard. Okay, not to mention I don't have a good webcam that can make the whiteboard happen. So one of these weird technology things is I don't have the non-technology to do the technology. So I don't think I can do a whiteboard lecture. Some of you wanted whiteboard lectures. So what I try and do is I do a computer whiteboard lecture. I type instead of write. My handwriting is horrible anyway. You don't want to see my handwriting. My typing is a lot prettier. But sorry about that. So I don't know if I can really address that one because I don't have it. Someone wanted a discussion board Q&A. I do have one, just no one ever uses it. But if you use it, I'll see it and I'll answer questions and you guys can talk to each other. It's up there though. So just no one uses it. Let's see. A couple of you said I spend a little bit too much time going over the homework. So maybe I'll make that a little bit shorter and then remind you that I always have office hours after class for every class. So I think I'll go with that one. That one I can actually do it. How do you put transpose symbol into Symbol Lab? You type in TRANPOSE in Symbol Lab. Okay, or another way of doing it is you just type in the matrix. So you don't need a computer to do a transpose. I hope you're okay with that, Ralph, right? That you know how to do a transpose without computer helping you. So that's how I do it. I just type it in. But if you want, you can actually use the transpose word, and that'll do it too. But it's a lot harder. Okay, it's a lot harder to type in the word transpose and then write down the matrix than to visualize the transpose of matrix and type that in, because the same amount of typing to do the transpose or the original. So there's no reason to write the word transpose. Okay. So, but there is a way, but I never use it because it's not easier. Okay. Multiplication is definitely easier with Symbol Lab, and so is inverse. Okay. A couple more things. Let's see. Yeah, some of you said it took too long to scan your work. I decided not to take off points if you were like a few minutes late because you were scanning, because again, we're in a new world. So I'll let you know. I'll do the same. Now, if you say it took 6 hours to scan your work, that's not okay. But if you turn it in 5 minutes late, then I'll figure, yeah, it was scanning time. Sound fair? So as long as it's a reasonable amount of time, I didn't take off points. Let's see what else. Those are the main things that you guys wanted to see. You like the fact that I have office hours after? That's not changing. I'm going to keep having office hours after. Okay. And I also have Tuesday and Thursday office hours. Some of you come, and I'm always happy to help you out. And I do check my email often, like more times than is healthy. So if you ask me questions, I can help you that way too. You know, outside of office hours. Any questions about the exam before we move to new material? Okay, let me go to new material. And I think today is actually a pretty easy day. Hopefully you'll find that it's easy also. And it's easy because I think just about everything we're going to do, especially in the first section, is intuitive. So let me just go through it. And I think you'll agree that we can make this work. Okay, so I'm going to start out with the properties of a linear transportation. I hate when they do autocorrect. Transformation. So properties of a linear transformation. Okay, so the first one is that if you have a linear transformation, by the way, just like before, remember, if I use capital A, what am I referring to in this class?
A matrix.
A matrix. Okay, if I use V, what am I referring to?
Vector.
Right. Now, if I use T, capital T, what am I referring to?
A linear transformation.
Exactly. So I hope you're all okay with that. So I don't have to write down, let T be a linear transformation. So if I write the letter capital T, that's the same thing as saying let T be a linear transformation. You okay with that? So it says that if you take a linear transformation and apply it to the zero vector, you get the zero vector. Is that surprising?
No.
No, not at all. But here's something that can get a little confusing. 0 is not equal to 0. Does that sound weird? So if you look at number 1, I see a 0 here on the left and I see a 0 here on the right. 0 is not equal to 0 necessarily. How come?
Because the 0 on the right is a vector.
Actually, so is a 0 on the left. They're both vectors.
I don't have an answer then.
The 0 on the right is a 0 matrix.
No, they're both vectors. Because remember, a transformation sends vectors to vectors. Any ideas?
It's a different kind of 0.
Right, but what kind are we talking about when you say
it spans a different subspace of Rn or
no,
Rn?
0 always, yeah, not quite that. It's that it may not be Rn for both of them. So in other words, the first 0 might be R6 and the second 0 could be R3. So linear transformations don't have to send a vector in 3 dimensions to a vector in 3 dimensions. They can send a vector in 3 dimensions to any dimensional vector. Does that make sense? As long as you fixed it forever. Because if you linear transformations, the range and the domain don't have to be the same dimensions. Any questions on that? And a nice useful example of that is a projection map. So for example, if you have the linear transformation from R3 to R2, where it just ignores the third variable, then the first 0 would be 0, 0, 0, and the second would be 0, 0. Is that clear? So I just wanted to kind of highlight a subtlety in this, is that the zeros don't have to be the same 0. Okay, number 2 is that the linear transformation on negative V is equal to negative the linear transformation on V. Any questions on that? And by definition, negative V is the additive inverse of V. So it's the unique vector W such that v plus w equals 0. And we call that negative v. Okay. And the third one says that t of a linear combination, summation of ci vi, is equal to the summation of cit of vi. So I think I'll at least prove a little bit of it. They're nice and easy. Any guess on how you prove the first one?
I mean, anything times 0 is 0.
Yeah, but we want to go backwards. 0 times anything is 0 is actually the way we want to write it. So t of 0 is equal to t of 0, the number 0, times any vector v. Pick your favorite vector. Do you agree that that's the same, that 0 is 0v?
Yes.
Okay, but now 0, this word gets so subtle. The first 0 is a vector in Rm. The second 0 is a number 0. Now a number 0 can get pulled out because that was a property of linear transformations, is constants can get pulled out of transformations. So that's 0 times t of v. Any questions on that? So that's the number 0 times the vector t of v. But a number 0 times any vector is 0. And we're done. That's the whole proof. Maybe I'll write proof of 1. Was that easy? So I like to do the easy ones. Proof of 2. Okay, well, we want t of negative v, which by definition is the special vector such that if you add it to v, you get 0. But we had a theorem that said that negative v is the same as negative 1 times v. Do you remember that theorem? That the way you get the additive inverse is you multiply by negative 1. But now we could take that negative 1 and we could pull it outside because it's a linear transformation and numbers can get pulled outside. So that is equal to negative 1 times t of v. But now we can use the theorem again that says negative 1 times a vector is negative the vector. One of the hard parts about this is to actually do the steps because it looks obvious, but actually you need to do this to prove it. Proof of 3. How do we do proof of 3? Looking for just a couple words. What proof technique am I going to use? Any ideas? Mathematical induction. You guys remember mathematical induction? How do you start mathematical induction?
Let something be something.
No. There are two main pieces of mathematical induction. What's the first piece? You remember? Probably been a while since you thought about proofs, mathematical induction proofs. So the first piece is you have to show it's true for the first case. In this case, n equals 1. Okay, or k equals 1. So for k equals 1, then the sigma part is silly if you're only adding one thing. So you don't even need the sigma. So then you just have t of cv Okay, if you want C1, V1. But what can I do?
You can write T of C1 plus T of V1.
No, there's a multiplication, not addition. C1's a number and V1's a vector.
So
It's the same as C1T, V1T, or T
Human T's.
V1.
Yeah, T of V1. And that's it. and that's the right hand side. Again, if there's only one to do, you're not adding anything. Do you agree? Adding, if you add all the numbers and your number is 5, there's no addition. Do you agree? If you only have one number to add, then there's nothing to do. Okay. So then I need to do it for K to show K plus 1. So we're going to assume it's true for K. And we need to show it's true for K plus 1, but that's easy. T of, and just so I don't have to do all the math typing, I'm just going to call it S for the summation. Are you okay with that? Actually, I'm not going to use the S. I'm going to use V1, C1, V1 plus ... plus CK, VK plus CK plus 1, VK plus 1. Okay. And what I can do is the following. I can say, well, I'm going to group the first K of them together. And I'm always allowed to do, that's called the associative property of vectors. Any questions on that so far? So then what's in this parenthesis is a vector. So I have T of a vector plus another vector. And I know I'm allowed to split up the plus sign if you only have 2. That's part of being a linear transformation. So that's going to be T of the first vector plus T of, and I can even pull the CK plus 1 out, T of VK plus 1. But now what I can do is I can use the mathematical induction, because now I'm looking, the first piece only has K of them, and that's the induction hypothesis. So that's equal to T, that's equal to C1 T of V1 plus ... plus CK T of VK, and then plus our last term, which was CK plus 1 T of VK plus 1. And that's the proof. That's what I needed to show. So it's done by mathematical. So it's true by mathematical induction. All right, MI for mathematical induction.
So would mathematical induction basically be saying, assuming that this is true, and then you show that it is true?
You're showing it's true for any K of them.
Okay.
And then you have to show it's true for K plus 1 of them.
Okay.
So it's kind of what the way a lot of people like to think of it is dominoes. You ever played dominoes?
Yeah.
And you're not just the game dominoes, but you hit the domino down and it knocks all the rest of them, right?
Yeah.
Well, if you know that the first K of them are going to fall, then all you have to do is show that the K plus first one is going to fall, and you know they're all going to fall. Does that make sense?
Yeah.
That's what this is.
Okay.
So you've shown, so you're assuming it's true that the first K of them fall, and then that last one, then we've proven the last one will fall. But you also you actually have to take your finger and go like that. That's the first one. you see?
Yeah, that makes sense.
Yeah. So that's kind of the domino analogy of mathematical induction. And I think it's the easiest way to think about it. Okay, so these are properties important to know. Not much we're going to do with them until, later we'll use them here and there. Okay. This is what we're doing next is, I wouldn't say silly, but easy. I hope they'll agree. Is that this is a definition. So what does it mean for two functions to be equal to each other? Just as functions. What does it mean?
They have the same domain and range.
No. X and x cubed have the same domain and range, but they definitely aren't equal to each other.
They produce the same result.
They have the same result for every single element of the domain. Does that make sense?
Yeah.
So for a linear transformation, if we have two linear transformations such that applying the first to a vector and applying to the second to the vector always gives you the same no matter what vector you grab, then we call those linear transformations equal to each other. Any questions on that?
And just to be clear, both S and T in this instance are equivalent matrices.
No, they're linear transformations.
Okay.
And I want to stick to linear transformations. It turns out that this week, it's good enough to say matrices because remember we had a theorem that every linear transformation is a matrix. Do you remember that?
Yeah.
But then remember those two words I said just a minute ago?
For now.
This week, yeah. So that's going to change. So if I leave the definition like this and don't use the word matrix, then this definition will work later on. If you use the word matrix, it doesn't work.
Okay.
Because not every linear transformation generally has a matrix, but every linear transformation from Rm to Rn has a matrix. Does that make sense?
Yeah, that makes sense.
All we're doing right now is from Rm to Rn. But that's going to change. So I want to kind of keep you, to let you know that it's going to change so that you're ready for it when it changes. Because it gets hard. It gets very abstract. Okay, so it's definitions. There's not much to say. It should make sense to everyone. I hope you realize it's obvious. Do you? That if you want to make it equal, then it better be equal for all of them. Okay, here comes the next definition. Also really obvious. Remember, linear transformations are functions. And hopefully you all know that if you had f little dot g of x, that's f of g of x. Do you remember that from functions? Well, linear transformations are functions, so you just say it. So we use the same notation, and that is s dot t of v is equal to s of t of v. Or s composed with t of v is s of t of v. Any questions on that? Again, there's not much to say here, but we have a big theorem. And this theorem is the point of matrix multiplication. And that is if s of t, the first thing, s of t is a linear transformation. Okay. And if A and B are the matrices for S and T, then A times B is the matrix for S of T. So this is huge. And the funny thing is, yes, it's a theorem, but it's the reason why we define multiplication of matrices in such a weird way. The whole point of having that, way of defining multiplication of matrices to be these dot product things is so that we can have this theorem. Because you could define multiplication using component wise. There'd be nothing wrong with that, if the original mathematicians did that. But the problem is, if you think of linear transformations as matrices and vice versa, then it'd be nice if multiplication was composition. And this works. Any questions on this? Any questions on this big theorem? Okay, the proof is a little messy, so I think I'm going to skip the proof on this one because we have another section to go that needs to be talked about. But you can look in the book, and the proof is there, and it uses the definition of multiplication. But any questions?
This S dot T is like function composition, like
Yeah.
f of g of x.
Yep, it's not even like, it is.
Okay.
Because remember, transformations are functions, right? There's a domain and a range, it's a function.
Okay.
So truly, S of T of X is composition of S of T.
Okay.
And which means that you need to do everything you're used to doing, which means that function composition is read right to left. Right? You apply T, then you apply S. Do you remember that with functions?
Yeah.
So same thing is that when you have composition of functions, you got to treat them as functions, and linear transformations are functions. That's all this is saying. Okay. Any questions on that? I think maybe I'm going to prove the first part, but I'm not going to do the multiplication part because the first part is actually not too bad. Okay. So to show it's a linear transformation, then what we need to do, actually, I don't need to go insert. I can just copy and paste. I need to take S of T and apply it to what? Who remembers?
To a vector?
Yeah, not a vector. I mean, a vector, but a messy vector. Do you remember what vector? AV plus BW. Do you remember that? And what am I trying to do? What do I need to do?
We need to find the matrices for S and T.
No, don't need any matrices.
Use our properties of linear transformations.
Yeah, in particular, we need to split up the pluses and we need to pull out the A's and the B's, or the plus, right? Split the plus and pull out the A and B. So we do that one step at a time. So that is equal to S of, by definition, T of AV plus AV plus BW. Any questions on that? That's by definition, that's true. Okay, but then T of AV plus BW, because T is a linear transformation, I can split up and pull out. So that's going to be S of AT of V plus BT of W. Any questions on that using the linear transformation property for T? Okay, but now I can use the linear transformation property for S because T of V is a vector and T of W is a vector. A and B are still constants. So that means I can split those up. And I think on the next line is probably best. So that's equal to A S of T of V plus B S of T of W. But that's equal to A times S of, now I gotta get the of, yeah. there's the of T of V plus B S of T of W. And that's the proof. Because I've now pulled out the A and I've split and the B and I've split up the plus. Any questions on the theorem? I proved the first piece. I only have so much time to do everything. Everyone good with that? Okay, here comes the next one. And again, all I'm going to do is say, hey, S and T are functions. And we know what it means to be inverses, right? Remember, F and G are inverses if F and G of X is X. And G of F of X is X. So similarly, S of T is equal to T of S. Okay. And that's equal to I. Now, probably a better way of doing it is, let's do it this way. S of T of V equals V, and T of S of W is equal to W. This might be a little confusing. Why did I need to not use V on the second one?
Because they're not variables, they're vectors.
Right, but I can't use V. I use V on the first one. You want to see? Because S and T don't have to have the same domain. It turns out. Now, it turns out you can prove that they do, but at least in theory, they don't. So basically, it's the same theorem, same definition that we had for functions, because they're functions. If you compose them, you get back what you started with. Isn't that what inverses are for functions?
Yes.
But here's the beautiful thing. And that is if S and T are inverses of each other, and A and B are matrices for S and T respectively, then A and B are inverses of each other. So if you know the inverse, if you know the matrix for S, and you know that S and T are inverses of each other, the matrix for T will just be the inverse. Okay, which shouldn't be a big surprise, is it? The inverse matrix is the inverse function. Okay, so I don't have time to prove it because, again, we only have a half an hour left and we have another section. I want to make a note, though. I found this out yesterday when I was writing out my notes, is that before yesterday, I don't know if, did any of you read the book, especially the LibreText version of the book? Okay, if you do, then, and if you tried to read ahead, you realize the section was missing. So I actually emailed the LibreText people and they put it in. So I apologize if you didn't see it. Now it's there. Just let you know. So if you printed a print copy, for example, at the beginning of the quarter, then it was missing that section. And now it's not. So it's in there. So one thing about me being part of the group is that the LibreText group is that if I ask for something, it gets done pretty quickly. Okay, so sorry about that in case anyone noticed. It looks like no one noticed anyway, though. All right, what I want to do now is I'm going to show you a program. Okay, can you all see the screen?
Yes.
Yeah, you should be able to see it. So just to let you know, this is a program I coded. This is a lot of work, by the way. Okay, and And what I did is I coded a program to show what happens to the XY plane upon a matrix transformation. And I'm going to let you know that for what we're doing now, this matrix, we're going to look at the 2 by 2 piece of this matrix. Okay. The 3 by 3 does matter. And I think I'll talk about it at the end a little bit. But we're going to look at it. We're going to ignore the rest of it. The zeros, the last column and the last row. And we're just going to look at the matrix, the 2 by 2 matrix. Okay, first thing, and I'm hoping you can all answer this question. If my linear transformation is 1, 0, 0, 1 as its matrix, what do you think it's going to do to this rectangle, this square here, if we apply that linear transformation to it?
Nothing.
Yeah, better nothing, right? So if I hit transform, notice what you see? How's it changing?
It's not.
Yeah, it's not. Okay. On the other hand, what if instead of a 1 here, we made it say a 1.2? What do you think is going to happen now to the XY plane when we apply this matrix to it?
It will be a bit bigger.
Okay. The whole thing, it turns out, won't be bigger. So let's do it, and maybe you'll see. I'll transform a few times. What happened?
It increased the value in X.
And not Y.
Yeah.
And that's because what this first column is the X basis vector, and the second column is the Y basis vector. So the Y basis vector is not changing, but the X is. Do you see that?
Yeah.
Okay, and I could do similarly. How about 1.1? And I can hit animate. What do you think is going to happen now?
It's going to decrease in X and then increase in Y.
Not quite. It's going to do nothing to X, but increase in Y. Because again, it's the identity for X. So if it transform, see what's happening?
Yeah, makes sense.
Yeah, so Y is getting bigger and bigger and bigger. Okay, so those are some easy ones. Let's hit reset. What if they were both 1.1? What's it going to do?
They're going to grow X and Y at the same rate.
Yeah, and what's going to do is you're zooming in, basically. It's going to get bigger and bigger. So let's do it. And do you see that happening?
Yeah.
Okay, so notice that when you have a linear transformation, and in particular, a matrix, and you apply it to the XY plane, it adjusts it, it changes it. Any questions on that? What if instead, let's say I made this one a negative one instead. What do you think is going to happen?
It's going to invert over the axes.
Yeah, let's do it. So that's going to reflect across the x-axis because it's changing y. It doesn't change x, it only changes y. Do you see that? Okay, and as you might guess, if I make the other one -1, what do you think is going to happen?
Same thing, but with respect to the y-axis.
Yep. And there you go. Okay, if I make them both -1, what do you think is going to happen?
It's going to be in quadrant 3.
Yeah, or it's going to flip one at a time. Okay, so each time is applying. So it's going to change, it's going to reflect across the origin. Do you see that? All right, now we're going to get more difficult. How about 0.707, 0.707, negative 0.707, and 0.707. Anyone recognize the number 0.707?
Cosine something.
Uh-huh. Mm-hmm. Cosine of, what's the something? And also sine, by the way.
Pi over 4.
Yep, pi over 4. So let's see what happens. What's it doing?
Rotating.
Yep, rotating about the origin, angle pi over 4. Any questions on that? Now, instead of 707, let's say we did 0.866, 0.5, negative 0.5, and 0.866. I think that's the numbers. What do you think is going to happen now? Any guesses?
Rotate the other way.
It's the same way, but it's not pi over 4 each time. Do you see that? It's pi over 6. Because you may or may not remember, but cosine of pi over 6 is 0.866 and sine of pi over 6 is 0.5. Any questions on that? So what this allows us to do is say, if I want to transform the plane by rotation or reflection, or by dilation, or by expansion, then I can apply a matrix and it'll do it. Any questions on that idea? Okay. Where do you think this might be used in the working world? What job would use this?
Computer graphics.
Yeah, in particular, yeah, and a computer animation. So if you're a game designer, computer game designer, this is how you do it. So if you want to move the thing, then you can rotate it. We can rotate it. You can reflect it. I will show you something just for fun. Let me reset. Is the easiest. What do you think is going to happen if I take that 0 and make it a 1? Any thoughts? I'll just hit animate and you can watch. What happens?
It's heading towards the z-axis.
Yeah, well, it's not heading, there's no z-axis here. It's going to the right. Do you see that? And similarly, if I make that 1 a 0 and I make the other 0 a 1, it goes up. Okay, so I'm going to tell you this, although I'm not going to prove it, but if you take the x, y, z axes in 3 dimensions and apply a 3x3 linear transformation and then project it onto a 2-dimensional plane, this is how you do it. Okay, so if you want to be able to move things left to right and you want to have perspective of a camera or something moving, or an eyeball moving and seeing the kind of vision of the world, this is how you do it. And again, any of you ever played a game that had 3-dimensional graphics?
Yes.
This is how you program it. Okay, I bet you never even imagined when you have a 3-dimensional graphics gaming thing that there's all this matrix linear algebra thing going on. Okay, because you were just having fun playing the game. Sound right? But if you want to, be a game designer, this is how you do it, if a programmer. So it's kind of cool stuff. It's a nice application. I can only get into so much. Any questions on this application? And I had a fun time programming this. Coding this was not that easy, but it was fun. Okay, so let me go back to the lecture notes, basically to formalize what I just did. Okay, so the first thing is these are just theorems. And that is if you want to rotate by an angle theta around the origin, this is the matrix. Read as columns cosine theta, sine theta, negative sine theta, cosine theta. And that will rotate it. And you choose your angle and it makes it work. By the way, what if you choose the angle 0? What's this matrix going to be?
The identity of a 2x2.
Yeah, and it better be. If you rotate it by angle 0, you're not doing anything. Do you agree? Okay, so that's just a note. That should be obvious. But whatever angle you want, you plug in, you get a matrix out of it, and then that's your rotation matrix.
If you want to change the direction in which you're rotating, do you change the signs of the functions inside?
Yeah, so you can rotate it by a negative angle.
Okay.
So it's not the functions. So if you want to rotate it, clockwise by pi over 3, then you let theta be negative pi over 3. Because that's clockwise pi over 3. Does that make sense?
Yes.
Yeah, so basic trig, but you have to think about it. And sometimes it's like, oh yeah, I haven't thought about that in a long time. But clockwise is a negative angle and counterclockwise is a positive angle. So that still works. And one of the nice things, check this out. What if you want to rotate by pi over 3 and then, or let's say rotate by angle A and then rotate by angle B afterwards. But you want to kind of do them both. Do one, and now it's rotated a bit, and you want to rotate some more.
You put it in sequence and series?
No, it's much easier than you're saying. So what you do is you just take cosine of A plus B. Sine of A plus B. And then negative sine of A plus B. And cosine of A plus B. All right, but there's another way of doing it too. And that is the following. Well, you could rotate it by A first by just putting A in. And then, well, if you want to rotate it again, we had already that if you want to compose linear transformations, that's matrix multiplication. So then you do the B. And remember, you have to read backwards in function composition. So you read backwards in the matrix multiplication also. And that'll give you actually the same thing, right? Because if I rotate by angle A and then I rotate by angle B, well, guess what? I've just rotated by angle A plus B. Anyone lost on that idea? Any questions on that? The interesting thing here is the following. Oops. What just happened? There we go. The interesting thing is, if I do that, then I'm supposed to multiply this. This gives me cosine of A, cosine B. And then minus sine A, sine B. And then the second one is going to be cosine A sine B. And then plus cosine B sine A. And then if I do the others, I'll get basically the same thing, same idea. I'll get cosine B. Let me just copy and paste. I think it's the easiest. So if I do the others, I get cosine B sine A with a negative, and then a negative for the other one. And I get that. Any questions on the matrix multiplication? Now I just proved something. What did I just prove?
Trig identities.
Yeah, the sum of angle formula for trig. All right. I don't know if you remember the proof of the sum of angle formula for trig when you had it in trig class. It was brutal. Do you remember that?
Yeah, I have a picture of it.
The proof?
Yeah, it was gross.
And this is not gross. It's matrix multiplication and you're done. And that's the sum of angle formula. That's it. It says the cosine of A plus B is the cosine of A times cosine of B minus sine of A times sine of B. Any questions on that? Isn't that beautiful?
That's wild.
Yeah, it's pretty cool. Okay. And by the way, there's an even easier way of doing this, of this proof. That's totally different. It's not linear algebra, so I won't do it. But that is using complex numbers. And I'm not going to do that today. But someday in your life, you might see it. But this is the linear algebra way of proving the sum of angle formulas. Okay, and it works. We got sine and cosine, or cosine and sine, just by reading the first column. All right, the next thing is, now what we want is consider the line y equals mx. And reflect about this line. What is the matrix of this linear transformation? Any questions on the question? So again, you draw a line in the xy plane, and then you take a point, you reflect it across that line, and that's your transformation. And that turns out to be a linear transformation. How do we find that matrix? Any thoughts? No idea? Okay, so if you want to find it, what we do is we see, well, if it's a linear transformation and we want the matrix, we need to see where it is going to take 1, 0, and where is it going to take 0, 1, because that's how you find a matrix. Find out where it takes a standard basis. So T of 1, 0. And where does that go? How do you reflect across a line? Any questions on the question? And this is where I'm going to have to do some drawing. By the way, this is the best I can do with whiteboard. It's going to be my kind of like, oh, actually, yeah, so I'm going to have to reshare and do whiteboard. Maybe I'll do whiteboard this way. Let's see if it'll work. There is kind of a whiteboard, but it's really hard to use. I think annotate. There we go. Draw. Okay. So here's my whiteboard. Okay. And we have some line. and we're going to reflect across that line. Any questions on the idea? So how do we reflect across the line? Well, we want to take the point 1, 0. And we're going to reflect it across that line, which is going to land somewhere over here. Any questions on the picture? Okay, so now that we want to do that, we got to see, well, how do we do that? How do we get there? How do we get to this other point? Any thoughts?
So we need a decrease in our value of x and increase in our value of y.
Geometrically, how we can do it. Because decrease, that might be true, but we're doing it in general. Sometimes it's increased, sometimes it's decreased, and it's kind of messy reflection. But in general, what we do is we find this vector. And what we're going to do is we're going to take this vector here and subtract, and then we're going to, so we're going to take this guy here and move it across like this. So what we can do is we can take this line with this piece right here. Remember, we had a name for that. Who remembers the name of that? Of this piece along? Yeah, it's a projection. And we have a formula for projection. Remember that? So we're going to take the projection of the vector 1, 0 on this line, like so. And then we're going to add this piece. Any questions on that? Which is the orthogonal piece. Get the idea of the picture now? So let's find the projection.
Why do we use vectors instead of angles?
Because we need a matrix, the linear transformation.
Okay.
So the answer is, this is a linear algebra class, which is all about vectors, right? Vectors and matrices. So we're going to find the matrix by looking at vectors. Yeah, so we definitely don't want to use the angles. What we're going to use is the projection. All right, so let's kill that. And I may have to get rid of that, but we'll see. Okay, so projection. Let's do 1, 0. And let me remind you, because I didn't mention it, but we have y is equal to mx. Any questions on that? Now, y equals mx in general is the vector x comma my. Any questions on that? I write what x is, which is x, and then I write what y is. Oh, sorry, mx, not my. So the projection is going to be what? Well, we take the dot product. Okay. What's the dot product of x mx with 1, 0?
X.
Yep, that's going to be x over, and I think I need to write this in math symbols. So it's going to be x over, and what is the magnitude of the vector?
Plus or minus 1. Or the square root of 1.
Yeah, and actually the magnitude squared. No, it's going to be x squared plus m squared x squared. Any questions on that? And then we multiply it by x comma mx, because that's a formula for projection. Any questions on that? which is equal to, oops, there we go, which is equal to, well, notice that there's that x comma mx, you can factor an x out and you get an x squared, and then you can cancel the x squareds. So that's going to be 1 over 1 plus m squared times 1 comma m. Any questions on that? So we're getting there. Now what do we have to do? Same thing except with 0, 1, the other basis factor. And if I do it with 0, 1, then notice the dot product is now is mx. Magnitude is the same. Still have x, mx. So everything's the same, but you can have an m on the top. Any questions on that? Is that clear? And in fact, instead of the m on the top, I think it's easier to put a 1 on the top and then make this m squared. Let's see if I got this right. As I wrote this in my notes. Somewhere in there. Okay, so then we don't have a lot of time, but we can now write this as columns. We can realize that everything has a 1 over 1 plus m squared. So you can kind of pull that out. And let me show you the theorem. Let me do the following. Uh-oh. Clear. Okay, so here's the big theorem. And that is we get the matrix 1 over m squared plus 1. And after doing a little work, you have 1 minus m squared, 2m, 2m, m squared minus 1. And that will rotate the plane across the line y equals mx. And that's the rotation matrix, or reflect, I guess reflect is a better word. It'll reflect the plane across y equals mx. Any questions on that idea? Okay, and the other 3 theorems are the ones I kind of showed you in a picture. C0, 0c expands or contracts the plane by a factor of c. C0, 0, 1, it's going to expand or contract the x-axis by a factor of c. And 1, 0, 0c expands or contracts the y-axis by a factor of c. And those are how you take the xy plane and transform it with a linear transformation by expanding, contracting, rotating, reflecting, etc., etc. And if you want to do an expansion and then you want to do rotation, you just multiply the 2 matrices, and that'll always work.
So it changes the plane, not the functions on the plane, correct?
What do you mean functions?
Like, so in that last example we just did, we were looking at the line y equals mx. We didn't change anything about the line y equals mx. We changed the plane around it, correct?
So y equals mx is the mirror.
Okay.
And so if you start with a point, the question is, where is it on its mirror reflection? Yeah, that works?
Yeah.
The mirror doesn't change because it's the mirror. Do you see?
Yeah.
Yeah, so, right, and so if you do it 6 times, and it's, if you keep using the same matrix, and it's the same mirror. Do you see how that works?
Yes.
Okay, but I'm out of time. That's why I kind of rushed at the end. So I'm going to stop the share, stop the recording.